Okay, now I can answer. What's the question?
Ya, şu ana kadar gördükleriniz dimension reduction diyebilir miyiz bu
No.
şeylere?
So I can give you a rough picture of what the hidden layers in neural networks are doing. So let's see how to put this. So the simplest machine learning algorithm that we can conceptually is k nearest neighbors, let's say, nearest neighbors algorithm, right? So how does that work? You have a new input. A new input x comes in, you compare with existing inputs, let's say you take the dot product with existing inputs, and then you find the closest match. And that becomes, the class of that closest match becomes the answer, right? So now let's compare this with a linear model, like a perceptron or a softmax model. What are we doing there? So KN, here's the query, and here's training set. We basically take a dot product of this query with every element of the training set, and whichever is the closest, we assign that answer. Okay, so what does a linear model look like? Again, the query comes in as a vector, and we have only one weight vector that we take a dot product with, or one weight vector per class, I should say. So each class, let's say, okay, so let's say we have 4 classes. So 4 classes, the W matrix looks like this. So this corresponds to taking the query X and dot product it with each of the 4 vectors here and pick the highest scoring one. Now, I claim that there is a great deal of similarity between these two. Right? So in each case, we're taking our X, we're taking the dot product with existing vectors of the same dimension. In the nearest neighbor case, we're basically picking those vectors from the training set examples. In the linear model, we're actually learning 4 vectors, let's say, to take the dot product with. And then we're picking the class that class of the dot product that gives us the highest score. Right? So if you look at it this way, then linear models could be seen as prototype learning. What that means is that for a linear model with 4 classes, you're basically learning 4 prototypes. Each of the rows of that W could be seen as an instance in your instance space, X space. And in fact, if we probably train a linear model and plot the individual rows of W, they will look like numbers. Okay, I didn't do that, but we can do that really easily. And you basically compare your X with each prototype and you assign the highest scoring. Okay? So we're basically creating sort of made up instances. They don't come from our training set, but we derive them from our training set as an average 5 or as an average 7. Okay, so what does a neural network do? So a neural network takes X and converts it into a higher or lower dimensional vector, H. Okay, so each element of this H is basically a function of all the elements of X. So we can see each element of this hidden vector as a feature of the input. We're computing H different features of the input, and we're hoping that these features will be more useful in deciding the class. So you can do feature engineering by hand. You can say, oh, I'm going to take the x features, and then I'm also going to take their squares and their logs and their exponentials, and I'm going to take pairwise multiplications of them, etc. So people used to do a lot of feature engineering of that sort. Or you can basically tell the machine, I don't know what features are important, you come up with them. So a neural network is basically a adaptive feature machine. It discovers features that are relevant to make the decision that you're trying to make. Okay? Okay, so that's the little summary of the different learning techniques. I can also show you, kernel machines and SVMs and other things in this picture if we have time later. Any other questions before we get started today? Okay, so we started talking about RNNs last time, and you're going to have an RNN lab tomorrow, so you need to be able to write your own code. So I thought it would be useful today to go over some examples of RNN models, and we're going to go through a classification model, a sequence classification model, a sequence-to-sequence translation model, and 2 language models with different mini-batching and other techniques, and try to learn the details of how to code these systems so that you can do your lab tomorrow without difficulty. Alright, so let me first start. These are all, by the way, in the KNet source, so you can look at them at home when you go. Let's first start with this one. This is basically a review of yesterday. So remember this picture as the picture of a simple RNN. If you don't count this cycle, the feedback cycle, this is the same as an MLP, right? So regular feed-forward neural network. The cycle makes it a recurrent network and allows it to carry some memory. We saw this piece of code yesterday. The difference between an MLP and a simple RNN, or Elman network, is just that we have an additional hidden vector coming in as an input, and we also have the hidden vector updated going out as an output. Everything else is the same. And when we're multiplying, when we're doing our first matrix multiplication, we basically do it with concatenated input and hidden vectors. Okay? So, yeah?
So, in KNet, you offer an initialization and a forward function.
Yes, we're going to talk about those.
Yes.
I haven't told them how to use them yet. It's coming. I do want to briefly mention the order of these multiplications and why I did it instead of weight times input, why I did input times weight. So let me talk about that. So far, whenever we talked about models, we always had weights multiplying the inputs from the left. Okay, so this is how I drew them. So this is the weights for the first layer, and this is the weights for the second layer. So this turns this into x prime, this is x double prime, etc. And then at some point you get a y. Okay, so this is basically multiplying from the left. Now we can rotate this thing and reflect it whatever, 90 degrees, and have everything go the other way. So how would that look? X would be a row vector, or a bunch of row vectors, and W would be standing on its side, and I would get x prime transposed here, and W2 transpose, 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 and this would be double prime transpose. Okay, so I would basically, I could get everything transposed, in which case I would write everything as x times w instead of w times x. At the end I would find the same numbers. Okay? Now why would you do this one way or the other? It turns out, if you're going to deal with LSTMs, one way of doing them is slightly more efficient than the other way. Let me illustrate. Where is it? So this, and then we saw, okay, so here's the LSTM that we saw yesterday. Okay. Here is the mathematical description of the LSTM. Let's remember what these things were. So forget gate was something that we applied to the incoming cell vector in order to forget some of the entries. Okay, so the forget gate basically, as with all the other gates, it's actually a linear function of the incoming hidden state and the input passed through a sigmoid. Whenever we pass things through a sigmoid, we call it a gate because we have numbers between 0 and 1. And by element-wise multiplication, these numbers will let us forget certain things and remember certain things. So F is the forget gate. We later use it to element-wise multiply the incoming cell value. I is the input gate. We use it to forget certain things from the new input. Okay. So CT tilde here is the new input coming in. So the new input comes in and we pass it through a tan H this time, mapping everything to -1 and 1, between -1 and 1. So this is the new candidate. Okay? So if I want to forget everything in my cell vector and just remember the new input, I would use this. If I want to keep the old cell vector and forget the new input that I've seen, then I would just set all the FTs to 1 and all the ITs to 0. So by basically adjusting the different entries in FT and IT, I can control how much of the new input and how much of the old memory I get to retain in my cell vector. Okay? And then to convert the cell vector to my actual output, HT, I calculate another thing called an output gate. And the output gate is used to sort of suppress certain things and remove, output certain things out of the 10H cell thing. So that's the mathematical description of the LSTM. Any questions? So here's the picture description, here's the math description. Okay. All right. So here is the Julia description. Okay. So I tried to make it as close to the math as possible. So as a Julia function, an LSTM takes some parameters, some hidden state, which includes both the cell vector from the previous time step and the hidden vector from the previous time step. Remember that LSTMs have two internal state vectors that they pass through time. One is called hidden, one is called cell. And input is the input for the current time step, xt. Okay? It's not the whole input sequence, it's just one time step. So this LSTM function is going to simulate one time step of the LSTM. Okay? So here we see that the parameter is a pair made up of some weight vector, weight matrix and bias vector. And state is a tuple made up of the hidden vector and the cell vector from the previous time step. And then H is basically the hidden size. I have 2 here because everything is transposed. And then basically this whole transposing things is in order to be able to do this. Okay, so what's this? I'm concatenating the input and hidden, and then I'm applying a single matrix multiplication and bias addition to that. Okay? If you look at the math, there's 4 different matrix multiplications here, right? So There's one here with the forget matrix, one here with the input matrix, here's the cell matrix, and here's the output matrix. So there's 4 different matrix multiplications in LSTM. Each of these matrix multiplications actually multiply the exact same thing, ht minus 1 xt, right? So every matrix multiplication here is applied to the same 2 vectors concatenated, okay? Now, it turns out that doing 4 separate matrix multiplications is more expensive than doing a single matrix multiplication and then dividing up the result later, okay? So, let's see if I can draw that. So here's the here's my input x coming in, and here's the hidden ht minus 1, and this is xt. So I concatenate them into this row vector, and then I basically multiply that with this big matrix, okay? And this matrix is going to have 4 separate sections, okay? And therefore it's going to give me, you know, the output in 4 separate sections we can think of. And the first section is going to contain the weights for WF, WI, WC, and WO. Okay? So if I concatenate all these W matrices together, since they're all multiplying the same xt, ht minus 1 concatenated vector, I can do this whole thing in 1 matrix multiplication, which is cheaper. And this brings me to why we want to lay things on their side. Julia is a column major language, so its array storage is column major, so it stores columns consecutively. So if you look at the linear memory organization of this whole array, so this whole column is together, and then the next column comes in, and then the next column comes in, etc. Okay? So that means after this matrix multiplication, if I want to separate my forget gate, input gate, cell gate, output gate from each other, okay? If they're basically laying on their sides like this, if they're aligned like this, I can basically just do subarrays, okay? Because all of FT is consecutive in memory, all of IT is consecutive in memory, so I don't actually have to you know, allocate new arrays and copy things over and shuffle things around. So in general, in a column major language, if you have a piece of matrix like this, it's easier to divide it this way. It's much harder to divide it this way, okay? Because in the second case, what I need to do is, since inside the memory this whole first column is consecutive, I need to take the first third and copy it somewhere, and then I need to take the first third of the next column and copy it somewhere, etc., etc. So there's a lot of copying and chopping up involved. Whereas in this case, you can basically just address a subset of the array. Okay? So with these 2 tricks, we can get a fairly okay, I don't know what I did. Oh, it's still there. Interesting. This happened to us before, didn't it? I wish I knew what. There we go. Okay, you guys still see it? That's the LaTeX code for that math. Okay. So that means with this one multiplication, I'm computing all 4 gates, or at least the linear portion of all 4 gates. The bias is also a single vector. And then over here, I'm splitting it into the 1 to h, 1 plus h to 2h, 1 plus 2h to 3h, 1 plus 3h to 4h. Remember, h was the size of our hidden vectors. So I'm sectioning it into 4 different pieces. I'm applying the nonlinearity, sigmoid in 3 cases and tanh in 1 case, and those give me my 4 gates. Okay? After I get my 4 gates, then I do the typical LSTM operations of this operation, the new cell calculation over here, cell times forget, in-gate times change, and then I do this computation, the new output hidden equals out-gate times tanh cell, and I return my 2 hidden vectors, hidden and cell. Any questions about this implementation of LSTM? Now, we'll almost never use this because this is infinitely slower than the built-in cuDNN LSTM, but at least you should see it once. And in case you want to change something, you want to implement a module that's not LSTM, the way it's implemented in cuDNN, then you can actually take this code and start fiddling with it. Okay? Okay. And then this talks about the sequence-to-sequence model, which is not the easiest one, so we're going to pause this for now. And we're going to start with a simpler example. Yes?
The other LSTM type that you said is faster. Why is it faster? Is it because it's on GPU or?
No, everything is on GPU. But the cuDNN library basically has reduced all these different operations into probably a single CUDA kernel call and optimized them somehow, so it's about 5 times faster, as did that. Okay, so in this example, we're going to do some sequence classification, and the problem we're going to solve is sentiment detection in movie reviews. Okay, so we have a data set that basically has movie reviews from IMDb, each of which has been already converted into tokenized, etc. And we're going to read a movie review. At the end, we're going to decide whether it's positive or negative. Okay? So let's see if we can understand this piece of code. So these are some common parameters. What's going on? Okay. Now let's look at this. Your friend was asking about this RNN forward, the cuDNN implementation. This is using the fast implementation. So when you're using the cuDNN package, you basically initialize your model using RNN init, and then you do your prediction using RNN forward. Okay, so there's 2 commands that we need to learn, RNN init and RNN forward. So let's start with RNN init. First of all, let's figure out what it's doing. Okay, so here is RNN init. RNN init basically takes 2 mandatory arguments, your input size and your hidden size. These are the sizes of the X vector and the H and C vectors, okay? And a bunch of options. And it's going to return an RW pair. R is a struct. You don't worry about what's inside R. It basically keeps all the meta information about this particular RNN, whether it's an LSTM or a GRU, what are the sizes of various things, etc. So it's just a struct. And W is a weight array. And RNN init puts all the weights into one array. just like we combined the 4 weights into one matrix, RNN init goes even further and puts the biases in there as well and all the other necessary weights into one big weight array, which is W. And then let's look at the various options that we can give RNN init to initialize different types of RNNs. The most important one is the type. So by default it's LSTM, but it can also be used to implement LSTM, GRU, I mentioned before, and ReLU and TANH. These are simple Elman networks, sort of the MLP type networks that just use the ReLU nonlinearity and TANH nonlinearity. Okay, so we have 4 types of RNNs implemented in this. Second, number of RNN layers. So just like MLPs can be stacked up on top of each other, RNNs can also be stacked up. So by default we're going to use a single layer, but you can use more than one layer as well. When you use more than one layer, what happens is there is things going on both in time and space, so it might be better if I draw it. Multi-layer RNN. So here's the bottommost layer. Takes a H, let's call it H1, H1T, XT, and outputs the new H1T. Okay. This output is also used, this hidden is also used as an input to the next RNN layer, which has its own T, this is T plus 1, H2, T plus 1, and you can go as much as you want. This has its own, each RNN layer has its own thing, own hidden going on. In case of LSTM, they have HNT, H3, T plus 1. So this is for one time step. One time step, XT comes in, the first RNN processes it, it passes its hidden both to itself for the next time step and to the upper layer. The upper layer does the same thing, the next layer does the same thing, and then we come to the next time step and XT plus 1 comes in, and similar things happen. Okay, so this is a multi-layer RNN. Any questions about this? Is this clear? So again, if you think about it, if I didn't have these horizontal arrows, this would just be a multi-layer MLP. Right? So input comes in, there's a bunch of layers, and then there's an output at the end. So we can call this output YT. Here's YT plus 1. The only difference is there's these hidden vectors that get passed from one time step to the next, and each layer has its own hidden vector being passed. Okay. One side note that you won't need now but might need in the future: when you're applying dropout to RNNs, it's not a good idea to apply dropout to the hidden vectors being passed to the next time step. Okay, so that actually hurts performance. But you can apply dropout to the vertical arrows, just like we're doing in MLP. You just don't want to hurt passing information through time. It's okay to hurt the information passed through space.
So if it's a single layer RNN,
There is no dropout.
from X to H? From
You can actually apply dropout to X. Dropout to X. Next, we have bidirectional. Let me draw a picture of a bidirectional RNN. So normally, I think this is what you're going to work on the lab tomorrow. Normally, RNN takes a sequence and processes it from left to right. So these go in. So that means that, for example, this particular unit here has all the information coming from x1 and x2, but it doesn't have the information coming from x4 and x5 yet, because the arrows only go to the left. Now, let's say you were trying to do something that required context from both sides. For example, I was going to assign a meaning to this word, or decide whether this word is part of a named entity, or decide whether it's a noun or an adjective. In all of these problems, these are all tagging problems, information both from the left and from the right might be useful. So what do? I actually create another RNN, which goes the other way. A backward RNN, which processes the exact same sequence from right to left. So the inputs are the same. This goes there, this goes there, this goes there. Okay? Now, so this unit has all the information about x3 and the left context, and this unit has all the information about x3 and its right context. What I can do is I can basically join the hidden states of these two units, and I can use that to make my prediction. Okay? So that way, when I'm deciding about y3, I have information from both sides, and this is called a bidirectional RNN. Yeah.
How do you make use of the output of the below unit?
So you combine it with the output of the above unit, you concatenate them, and that becomes the output at, for example, time 3. So the two LSTMs run independently of each other. They don't feed into each other, unlike the multi-layer one. They both take X, and they generate an H or a Y, depending on the type of RNN. And all you're doing is you're concatenating the outputs of the two RNNs, one forward RNN and one backward RNN. And you have to be careful to align them correctly so the outputs of the X3 are concatenated together.
Are you thinking of these vectors as, for example, a word representing a word?
Correct.
So,
X1, X2, X3, they're representing words.
okay, so it sounds like we're concatenating words.
No, because we're concatenating H's. H's are not words. H's are the outputs of the RNN, or the hidden states of the RNN. So an H vector going from the left to the right will accumulate information. Okay, so think of LSTM, for example. It starts with H0, let's say, and at every time step, it decides to put some of the information about the current time step into this vector, and keep some of the information coming from before, and it keeps going, changing this H vector over time, and at every step you have a new H vector summarizing everything that you've seen since the beginning.
So we need to make sure that the size of H doesn't change, right?
Yeah, the H is always the same size, yes, it's our hidden size.
I couldn't, when you're concatenating, the size grows.
For the output, when I'm making the Y prediction, I'm basically taking the H3s, H3 forward and H3 back, and I'm concatenating them before I pass it to the output layer. The output layer is separate from the LSTM. Okay, so maybe I should, let me talk about that. Input and output layers. Okay, so here's a plain RNN. Okay, and here is my input X, and here is the output I want Y. Typically, what's going to happen is that there could be a linear transformation that gets X ready to go into the RNN. Okay, maybe make it the same size as the RNN's own hidden size, for example. And also, typically there's a step that takes HT plus 1 and linearly, or maybe a single RNN layer, converts it into the output. For example, if the output of my RNN is a word, and if my vocabulary is 10,000 long, my hidden state is 100. So the output of my actual RNN is a vector of size 100. I need to take this vector and then convert it into a vector of size 10,000 for the softmax to decide which word to output. So that takes place in the output layer. So this is the output matrix, O, let's call it, and this is the input matrix. Okay? So you can have independently, separate from the RNN, an input transformation and an output transformation to connect X and Y into the insides of the RNN. So in the bidirectional case, you'll have two RNNs, backward and forward. They will generate two different hidden states, and this output matrix or layer is going to take the concatenation of those two and generate a Y. Is that more clear?
Yes. This time our output layers input will be the 2 times of the regular.
Yes, correct. In the bidirectional case.
Yes, and we don't make use of the below networks Y, right?
Yes, in the beginning I said there is a separate Y and an H, but in the architectures I'm going to discuss today, we're just going to think about H. Okay, so X and H t minus 1 go in, and there's a new HT that basically gets produced, and then how you convert that HT into a Y is the responsibility of the output layer, which I'm separating from the RNN now.
Okay.
Okay?
So that in this case, for example, when in a translation case,
Yes.
We are making use of H in 2 different ways.
Yes, it's carrying information to the forward time step, and also it's getting fed to the output generator. So this HT plus 1 and this HT plus 1 are the same thing. Okay? So you're right, we're making use of it in 2 different ways. We're both carrying it forward to the next time step, and also using it to produce our output. Yes?
What about this I, the input matrix? Is it, what kind of matrix?
So let's say my inputs are also words, so they're very high dimensional. They're maybe 10,000 dimensional one-hot vectors representing different words. I may want to create an embedding that's 100 dimensional, that's easier to work with. So I will have a 100 by 10,000 embedding matrix. I will multiply that matrix with my one-hot vector, which will choose one of the columns. If the one-hot vector has 1 in the ith position, then it will extract the ith column of my embedding matrix as the representation for this word. So that's usually, I is usually such an embedding matrix. Yeah.
In the bidirectional case, there is a forward and backward flow.
Yes.
So will we wait to make a prediction to these both passes to complete?
Correct. So you want the hiddens from both the forward and the backward to be ready, so that at position T you have 2 different hidden vectors that are waiting for you that you can concatenate and make a prediction with.
These 2 passes complete and we predict all the words at the same time?
Correct. All the tags get predicted after the 2 passes are complete.
What about the BPTT?
You don't care. KNet does it. Right? So as long as you can compute your loss, so it doesn't matter how you write your code, you're going to say, oh, first run the forward RNN, and then run the backward RNN, put all of these hidden things into a list, and then go over the 2 lists and concatenate them one by one, generate my Ys. In any order that you wish to write it, as long as it generates the right loss, BPTT will work. Okay, next we have dropout, which we, is the dropout probability. Skip input equals false. This is a badly named option. normally this RNN init actually generates the input matrix as well, the input embedding matrix as well. If you say skip input equals true, then that means don't touch my X, feed it directly into the RNN. Otherwise, it actually generates an embedding matrix for you and it trains that as well. Yeah.
If we skip input, what do we get in the VI section of the matrix?
VI section, what's VI?
I mean, the output of this RNN unit will be a R and V, right?
Yes.
that
Oh,
will
yeah.
be
So the weight array will basically not contain a matrix to multiply the X with. X is going to be directly used inside the.
The size will be smaller, or just are you have done it?
I think it's smaller. Yeah, or I don't know if it fills it with zeros or something, but I know it ignores that part somehow. I think the size is smaller. Yes.
So for an input to this structure, we are going to give a 1 hot vectors matrix?
Yes. Or we're going to compute our own embedding.
And specify skip input equals false.
Correct. So data type is float 32. We always use that for speed. Algorithm, detail, random number seed for initialization. WInit is a function that it uses internally to initialize your weight matrices. And BInit is another function that it uses to initialize the bias vectors. So by default, weight matrices are initialized with Xavier and biases are initialized with zeros. And you can also control whether the GPU is used or not. Normally, by default, if there's a GPU, it will get used. So these are all the different options of RNN init. Now, if you want the nitty-gritty details of what actually this RNN will compute, the formulas are down here. So for ReLU and TANH, let's just look at the first couple. We don't have to go through them because we've already done them. But so ReLU and TANH basically give us a simple RNN with activation function ReLU or TANH. So there is a W matrix that multiplies the XT input. There is an R matrix that multiplies the hidden state from the previous time. Somehow, for some reason, it actually has 2 bias vectors, which is dumb because obviously you're adding them. You could have had a single vector here, but probably because of the way they internally coded this, they actually generate 2 bias vectors. So this linear function of xt and ht minus 1 gets computed, TANH or ReLU gets applied, and that becomes your new h. That's it. That's the whole operation for these two. LSTM, we've already seen. It's very, very similar to the piece of code I showed you before. GRU, you can look at it in your own time. But these are the exact formulas which get computed by these 4 different RNN types. Yes?
So for example, the VI, WI in the first
Case?
yes, in the GRU case.
Yes.
In the input GRU. So it's actually 2 matrices multiplied, 1 embedding matrix and a regular input weight matrix.
You're talking about the skip input again?
Yes.
Yes. So
Default case.
I think in the skip input case, W is just the unit, identity matrix. So actually, that's true. So whenever we say skip input equals true, whatever the non-default thing is, that means, for example, in the first equation, we're going to assume there is no W, and we're going to add xt directly. So in that case, xt needs to have the right dimensions in order to be added to, r times ht minus 1.
Why would we have to directly assume, let's assume we have
So you have an input size and you have a hidden size.
Yes.
When you say skip input, that means the input that you're providing is already at the right size, namely the hidden size. You've already converted it from whatever one hot vector or large vector you have to a vector with hidden size, and there is no W allocated, and XT gets directly added.
Doesn't it make it, we didn't convert it to hidden size, but we converted it to embedding size?
In this implementation, that has to be the hidden size, if you're going to use the skip input function.
Okay.
Don't use the skip input function. I've never used it, so don't worry about it. Okay, there's a lot more important things that we're going to go through.
I thought it was on by default, that's why we read.
Skip input is not.
Oh.
The default is there is a W here, and this W size is determined by the two parameters you give RNN in it, which is the input size and the hidden size. This W will have hidden size as the output and input size as the input. It will convert the X into a H size vector. That is the default. Okay. So here's how we use this. Let's edit the model. So as I mentioned, two things get returned by RNN init. This, the specification of the RNN, some struct, and the weights. As input, we give it the input size, which I called embed size here, and number of hidden. This is the hidden size. And as RNN type, I specified GRU for this example. And then, for input matrix and output matrix, as I mentioned before in this picture, this is the input matrix. Oops. This is the input matrix, this is the output matrix over there. I basically initialize my own matrices. The input matrix basically takes max features, which is the number of the vocabulary size in the IMDb movie reviews. It's like something like 10,000. And it converts it into embed size, which I basically set to whatever I want. And then the embed size vector is still going to get multiplied with a W to convert it into a hidden size vector in the equations. So that's the input matrix. And the output matrix is going to take the HT that was computed, which has the dimensions number hidden, and output two numbers, which are basically the numbers, the scores for positive and negative review. Okay? So, to summarize in this picture, what we're doing is the actual XT is, actually, let me see what these numbers are again. Okay, there we go. So max features, 30,000. So basically, XT has 30,000 dimensions. It's a one hot vector with 30,000 dimensions, or maybe it's an integer that I'm going to use as an index. Okay, and that's going to get converted into a 125 dimensional embedding vector. Okay, so the output of this guy is going to be 125 here. And then the hidden size is a 100. So that means incoming here is a 100 dimensional vector. And then the inside the RNN, which is a GRU in this case, some type of computation is going to take place. And I'm going to get a 100 dimensional hidden vector output. And that's going to get converted into a two-dimensional score. Okay? Any questions about the dimensions going in and out of the RNN?
So in this case, it's positive and negative, the two-dimensional could be also one-dimensional.
Say it again? Yes, we could actually have a one-dimensional output. So since we're making a binary decision, you can actually have a single output and use the logistic loss function instead of having two different outputs. Any other questions? So this was actually a benchmarking example, so I had to code it the same way they did it in TensorFlow and PyTorch and everything else. And they used two outputs. All right, let's go back. Any questions about init model? So init model basically does all these allocation and then returns the RNN structure as well as the RNN weights, the input matrix, output matrix. Okay, so here's the next important thing, predict function. Insert cell above. So it uses RNN forward. So let's find out about this. As I mentioned, that's the second important function. Okay, so so let's look at its input and output. The input consists of R, which is the RNN struct that we got from RNN init. W, which is the weights for the RNN that we got from RNN init. Input is X. I'm going to talk about the shape of X in a minute, but X represents the whole sequence. It's not just one time step. RNN forward has the ability to handle the whole sequence at once. If you want, you can also call it, for each time step separately. That also works. But in this example, I think we're going to use it as a block. Optionally, we can also provide HX and CX, which are the hidden and cell vectors that we want the network to initially use. Okay? Cell vector is only used by the LSTM. The GRU, 10H, and ReLU RNNs, just ignore it. HX is used by all of them. And if you don't provide them, they're taken as zero vectors. So at time step 0, the initial hidden vector that comes in is taken as 0. Okay? All right. We'll talk about the optional keyword arguments later. Let's look at what it actually outputs. The output is a quadruple output, I guess, but we usually only use the first value. Y is the whole sequence output. HY out and CY out is the last states of the hidden and cell. And RS is some kind of buffer that the RNN needs for its gradient calculation that we don't need to worry about.
You don't need to keep track of RS.
No. You can ignore everything in the return value that basically is not Y. So now let me tell you what's the difference between HY, CY, and Y. And let's do a multi-layer RNN. HY, CY, Y. Okay. So we have X1, X2, X3. So HC0, HC0 go in, and they come out. And then at each time step, we also have Y1. Now, since there's two H's, I should call these 1, 0 and these 2, 0, right? So this Y1 is actually equal to the hidden of the second layer, H21. H21, HC21 is also passed forward here. C is optional. And finally, we have H and C with 2T here, and H and C with 1T over here. Okay. And here's the remaining arrows. Y2, Y3. All right. So normally, if we had a single layer RNN, we wouldn't need the HY and CY because, let's forget about CY. We wouldn't need HY because HY would be the same as the last Y. Okay? So what gets returned to us as Y is these guys over here. And what gets returned to us as H and C at the end are these guys over here. Okay? So I'm drawing this to show you that you only care about the HY out and CY out, the last hidden state and the last cell state, if you either have a LSTM, so you want to know about the cell, or you have a multi-layer network, so you can't just look at the last Y and figure out everything, because Y only is the output of the last layer. So that's the difference between the three different outputs. Okay. Questions about the outputs? Yeah.
Another question, but it also comes handy if you are dealing with like batches that consist of elements that are different lengths.
Yes, I'm going to talk about that in a little bit. Yeah, that's right. So normally I will ignore everything that's not Y in the output, so I'm not going to talk about it anymore, if I can help it. If you want HY and CY to actually be output, these two keyword arguments are for that. They're Boolean. If you say true, the HY and CY will be output. The last hidden and the last cell state will be output. If they're false, which is true by default, they won't be output. Usually you won't need them, so they won't be output. We'll talk about batch sizes later. So let's talk about sizes actually. So X is a 1 or 2 or 3-dimensional tensor. Okay? So let's talk about 3 dimensions first, because 3 dimensions is the simplest one to understand. XBT, which order physical? Hold on. XBT, yeah. So we have a 3-dimensional X. So here's the X dimension. The second dimension is basically a bunch of X's stuck together. So that's the B dimension. The batch dimension. So let's say you're basically having 10, mini batch size of 10. So B would be 10. And then the third dimension would be the T dimension. So this means we would actually feed the whole sequence at once. Okay? So those would be the dimensions of a 3-dimensional X input. You're feeding the whole sequence at once as input. Any questions? Okay, so if X has only 2 dimensions, then we basically take it as X and B. And sometimes it will have another interpretation if the batch sizes are changing, but I will, in this case, X are 3, here's X is 2. And if X is a single dimensional thing, it's just going to be a single instance. Okay, so single instance if 1-dimensional, a mini batch if 2-dimensional, and a whole time sequence of mini batches if 3-dimensional. Any questions? Now, whatever you give as X, you will get exactly the same shape as Y. So if you provide a 1-dimensional X, you'll get a 1-dimensional Y. If you provide a 2-dimensional X, you'll get a 2-dimensional Y, etc. Okay? So if you provided the whole input time sequence as X, you will get the whole output as a 3-dimensional tensor as well. Okay? Okay. So Y therefore has some sort of y dimension followed by an optional b and t again. The y dimension itself might be h or 2h. H is the hidden size. Why do you think it might be 2h sometimes? Yes, so if it's a bidirectional RNN, there is a forward RNN and a backward RNN. So since we concatenate their outputs, in that case, y will be 2h dimensional. Okay. The hidden tensors, the hidden cell values, both at the input and output, are going to have 3 dimensions. The first dimension is hidden size. The second dimension is batch. So if you have a mini batch, you need to have more than one hidden vector for each batch, right? And the third dimension is number of layers. So if you have a single layered RNN, then no problem. But if you have 2-layer RNN or 3-layer RNN, then you need to have 2 times or 3 times more hidden vectors, and that's represented as the last dimension. And as you can see, the last dimension also says either L or 2L. And guess why it can be 2L? If it's bidirectional. If it's bidirectional, then you need 2L different layers. It's an L, there's an L layer forward RNN and an L layer backward RNN, and each of them have their own hidden vectors. Okay? All right, now finally, I should mention the batch sizes.
May I ask something?
Yeah.
Why would HY out have a dimension? It's just the last.
Last time step.
Yes.
Yes, there is no time step dimension in the H. So the time step, there is no time step dimension there. The dimensions are the hidden size, the batch size, and the number of layers. There is no time there. Any other questions?
So if you feed whole sequence, we expect a whole sequence, right?
In Y.
In Y.
If you actually use the HY and CY outputs, they don't have the whole sequence, they just give you the last time step. Therefore, the hidden tensors that we use, H and C tensors that we use, never have a time component. They only have a hidden batch and layer component. Okay? Now, batch sizes. Where's my mini batching picture? There. Okay. So remember this discussion we had? If your sequences have different lengths, how do you mini batch them? Right? So I mentioned padding and masking and sorting. And number 4 I left out. It was the RNN forward solution. And here's the RNN forward solution. So first, in RNN forward, you sort the sequences in the mini batch so that the longest sequence is at the top. Okay? So let's say 6, 1, 2, 3, 4, 1, 2, 3, 1, 2. Okay? So this is time goes this way. And this is the mini batches. There's 4 sequences I want to put together into a mini batch, but they have different lengths. Okay? Now, what I do is I basically represent this as a 2-dimensional X. So my X input for RNN forward is going to be the X dimensions and each sum of EI dimensions, let's call it that. Okay? So what I'm going to do is I'm going to take these 4 X's and put them side by side, concatenate them, and then these 4 come next, and then these 3, and then these 2, and then this one, and then this one. Okay? So each of these x's in that order basically gets concatenated side by side into a matrix. Why matrix? Because each of these circles is a vector, right? So I'm taking all of these vectors and just concatenate them in that order. First batch, then time, into a 2-dimensional matrix. So what's going to be the dimensions of this matrix? The first dimension is going to be the x vector, and the second dimension is however many x vectors I have in all of my sequences. Okay. So now that I have a 2-dimensional x, how is RNN forward going to know that these things come from different batches? How many batches are there? So that's where the batch sizes argument comes in. So batch sizes, in this case, is going to be something like 4, 4, 3, 2, 1, 1. Okay? So notice that these are basically representing the size of the mini batch for each time step. So once you give me that x and those batch sizes, I know exactly what you mean. Okay? I know that the top guy actually goes 6 steps, the next one goes 4 steps, etc. from these numbers. So let's make sure I'm telling you the right thing. So if batch sizes is an array of non-increasing integers, it has to be non-increasing because I sorted everything. So when I'm going left to right, the actual batch size can only decrease. Okay? Actually, that's always true, even whether or not you sort it. So it gives us the batch size for each time step in the sequence, in which case sum of all the batch sizes should equal to the second dimension of x. Okay? And the output will be given in the same order. So the output y will have the exact same shape as this x, and will have the same order, etc. Except for the y dimension is going to be different than the x dimension. But the second dimension is going to be matching the x dimension. So that's the batch sizes solution to the RNN mini batching problem. Any questions? Okay, let's see some of these in action. I talked too much and didn't show you enough. Code running. So there is let's look at the predict again. Okay, so my weights, remember, was a triple that consists of the RNN weights, the input matrix, and the output matrix. So I separate them here. Indices. These are basically, my inputs are represented as integer indices. They're not one-hot vectors, but they're indices. So this is a B by T matrix, mini batch size by time. RNN input becomes becomes a X by B by T 3-dimensional tensor, and I get this by looking at the input matrix, which contains the embeddings. So let's see what the input matrix was. Oh, did I pass? Yeah, so the input matrix was this thing that basically converted 30,000 things to 125 things. So how do I represent this? Here's the better picture of an input matrix. It's a 125 by 30,000 matrix. Okay, and by representing all of my input words as integers, and looking up the various columns in this matrix, I can basically pick the embedding vector for each word in my input, and those become the data that I feed into the RNN. So these two lines basically do that. And RNN forward computes the output. And here, as you notice, I ignore everything else except the first component. The first component was the Y. That's the only one I care about. And Y is going to have HBT dimensions. H because Y has the same dimensions as the hidden. And B and T because I fed it at 3-dimensional X, I'm going to get a 3-dimensional Y. This is the RNN output. I want to convert the RNN output, which is a 100-dimensional 100 by B by T dimensional thing, into the actual 2-dimensional scores. And I do that by multiplying with an output matrix. Okay? And note the end here. What's this end for? It's the T dimension. Why am I just using the end? Because I gave the X as a whole tensor. I took the whole Y as a tensor. I only care about the last time step because this is a sequence classification problem. I'm trying to get whether this is a positive review or a negative review after having read the whole thing. So I don't care about any of the other Y's. I just care about the last Y. Okay? All right. So that defines the loss and its gradient. So let's actually apply this to something. This is going to load the IMDb data. Okay, so there's an X and Y for training, X and Y for testing, and there's a dictionary that comes in. So let's actually look at XTRN, what it looks like. It's a bunch of integer arrays. Okay? So 24, 52, 6007, these are each word codes for words. And this whole sequence here is one review. Okay? Yeah.
So so each review is of the same length in your model, right?
It's padded. So if you see the second one, you will see that it starts with a bunch of 30,000s, which is the padding token. So each review has been padded to become the same length, yes.
You don't care about masking.
That's correct.
So we didn't pad it. It was already.
Yeah. I don't know if I did it or if it was already like that.
RNN forward doesn't need padding.
RNN forward doesn't do padding. It doesn't recognize padding. You basically pad it and then give it to it, RNN forward. You can't do masking with RNN forward. You need to use batch sizes if you want to actually ignore the padded tokens. But if you don't care about ignoring the padded tokens, just pad everything and give a 3-dimensional X. That works. What does Y look like? Okay, so it's either 1 or 2 for each of these reviews. 1 means negative, 2 means positive. Can I actually see one of these? I think I can see one of these things. IMDb dict XTRN 1. No? Well, I could see these things. What's IMDb dict? I just want to see the text. Oh, okay, so I have to convert this into an array. So this is the actual word codes for every word. There's 88,000 things in this. Only the most common 30,000 of them were used to build the data set. All the rest was converted into some so let's say array equals array string .88584. Okay, and then MDB for key value in IMDb dict, IMDb array of value equals k, and then let's see. Okay, so that's the IMDb array. So now I can actually see one of my reviews, hopefully. XTRN1. Okay, sharp, engrossing, and perceptive examination of suburban angst and the limitations of the blah blah blah. Okay, beautiful review. Okay. Effective recommended viewing for Sarno fans. So this is just to show you that it's not made up. It's actually IMDb stuff. We initialize the model. Here's another thing that we haven't seen before. So if you want to use any training procedure other than SGD, each of the other training procedures implemented in KNet actually has internal state. They need to keep around some statistics on the weight updates. For example, Adam keeps around 2 extra arrays for each array that you're actually updating in order to keep the first and second order statistics. So what this function does, this optimizer's function does, is basically initializes those arrays. Okay? So you give it your weights, the type of optimization you want to do. In this case, I'm choosing Adam, and maybe Adam has a bunch of options like the learning rate and the other parameters. So you give those things, and it gives you a bunch of optimization structures, which will be used with, which will be used here. So here, what am I doing? I'm looking at XY TRN with batch size. I'm mini batching them. For each XY, I'm basically calculating the loss gradient of XY with that particular RNN specification. That gives me all the gradients for the weights. And then I call update with the weights, the gradients, and these optimizer things that I just initialized. Okay? This is how we use Adam and other optimizers. I'll actually have a lecture on all the optimizers in the future, but yeah.
The optimizer doesn't need the objective function in the level or something?
Say it again?
The optimizer function doesn't need the objective function.
Well, objective function is loss. And loss gradient was defined up here as the gradient of loss. What is that? Here.
The optimizer doesn't have it as an input, right?
The optimizer does not need it. The optimizer basically is the optimizer structure is the specification and the internal state variables of the optimization algorithm you're using for that particular array. It's just, you know, statistical information about updates. The actual optimization, the actual changing of your weights is done by this update function. This update function has all the information. Okay?
Then we're going to get the kind of optimal parameters. Then we need to have to see what's the objective function. And depending on that, we need to define them.
So okay, so there's 2 lines here. Which line don't you understand?
The first one.
The first one says
optimizer one, about.
Optimizers just allocates a bunch of arrays. You don't have to worry about it. Okay? These arrays are used by the optimization algorithms like Adam and Momentum, etc. So you need to initialize some empty arrays for these things to work, and that's what optimizers does. It doesn't do any optimization. It just allocates space for various optimizers to do their work. Okay? The actual optimization is done with these 2 commands.
Now the optimization that I meant was for optimizing the parameter that we're going to use.
Optimizing the parameter.
What we're going to choose a parameter to train the model.
A hyperparameter like the learning rate?
Hyperparameter, yeah.
Okay. And I'm choosing that here, for example, as the big constant LR, which was defined above.
I thought with optimizers we are optimizing the hyperparameter.
No, that's a hyperop. That's a totally different section of the KNet. So this is not a hyperparameter optimization, this is just regular optimization. Okay, so let's at least finish one example. I was supposed to do 4 this class, but luckily this is actually training really fast. I'm only going to go for 3 epochs. There is, how many examples were there? 25,000. 25,000 reviews. I'm using a batch size of 100, so 250 updates each epoch. Each epoch takes 10 seconds using this RNN forward. Before I started using RNN forward, using the LSTM implementation I showed you earlier, the same thing was taking maybe 100 seconds instead of 10 seconds, which was the fastest of all the frameworks that are not using cuDNN, but still the difference was big, so we had to add this RNN forward function into KNet. Okay, so 29 seconds, we're done. And let's test it on the test. After 3 epochs, accuracy is 85%. Okay, so 85% of the time, I can tell whether a review was good or bad, based on these words and these RNN weights. Okay, I'm sure if you fiddle with this more, you can actually improve the.
These reviews are not pre-processed, right? They are gold reviews.
They're lowercase, tokenized,
Randomization, stemming.
not stamped. We actually saw some one up here. Right, so this is what they look like. So it says limitations and stuff, so it's not lemmatized, but definitely lowercase and tokenized. Okay, any other questions? All right.
Is it possible to share the lab documentation before the class, like today?
You can write to the list, and if it's ready, the TAs will respond.
If we talk to the TAs, they said talk to the Hoja. I mean, 1 day is not enough for finishing the lab. It's not even 1 day, it's like 16 hours now.
Why isn't it enough?
It's getting harder.
Well, if you guys need an extension, I'll give you an extension. No problem. Okay. See you next week.